Okay, so now we get to actually dig in a little bit now to chapter 12, and we're just going to start off with scatter plots. And scatter plots are exactly what they are, just dots scattered. So we're going to talk about why they're so important. Okay, so in many studies, we measure more than one variable for each individual. Some examples are rainfall amounts, plant growth, exercise and cholesterol levels, height and weight, right? So we always like to see a relationship between, like, for the first one, it seems so obvious, right? The rainfall amount and plant growth. We need rain for plants to grow. So if there's a lot of rain, are plants going to grow? Is that a relationship? Yeah, it's a definite relationship. And I think we kind of know that's causation too, right? Water causes plants to grow, right? Um, so there are a lot of ways we can interpret these. They could be unrelated, right? One variable, the explanatory variable, could be used to explain the other. So we don't necessarily say causation. We say it's the explanatory variable of rainfall. So rain explains the plant growth, right? That explains it, right? Like, duh, it rained a lot. My grass is growing a lot, you know? So the explanatory variable is going to be explaining the other, which is the response, right? So the explanatory variable will be the rainfall, and the response is how the plants grow, right? The response to the plants have. So the rainfall explains the plant growth, and that just means that we need to somehow measure this explanation. And so, how powerful is the explanation? And so, we're going to actually measure how much the explanatory variable explains the response. How much does rainfall explain plant growth? Because other things can explain plant growth, right? Not You don't just need water, right? You need soil, you need plant food, right? So there's other little variables that we need to talk about. And so those variables outside the explanatory and response variable are called lurking variables. So let's go ahead and I did a very basic example I feel everyone can relate. A research studies of a group of elementary school children, the student's height and the student's shoe size. It is not reasonable to claim that the shoe size causes height to change because a lurking variable of age affects both of these two variables. So, what are we saying here? So the first thing we're saying, we're not denying we're not denying there's a relationship, right? There is a relationship um, between height and shoe size. Height and shoe size are related. For example, on a 1-year-old starting to walk, they definitely aren't going to fit in like their mommy's shoes, which is an adult size, right? Because they're little, their feet are little. And as they grow, their feet will grow too. And so we know that shoe size and height are related somehow. But how much does one explain the other? Does height explain the reason the shoe size increases, or does the shoe size increasing explain why someone is getting taller? Or maybe they're just related and it changes because of other factors, right? So, what are some of those other factors? Well, they mentioned age, right? What else could be factors that are lurking variables? So I could say, oh, he's tall. His shoe size is going to be huge. Well, what plays into that, right? So age, but what else? How about genetics, right? Right? I think those are two big things. So just because we have a relationship between two variables, it doesn't mean one causes the other, right? So um, height doesn't cause shoe sizes, just because they are related. So it's that this is like the one of the most important things we have to realize is there is a relationship between height and shoe sizes. And in the previous video, I mentioned there is a relationship between the amount of butter we eat and the number of divorces and the number of stars out there and the number of car accidents. But does one cause the other? Does the amount of butter I eat is going to cause me to have a divorce? And will me having a divorce cause how much butter I eat? It's silly, right? It's not, I know you're looking at me like I'm silly, but there is a relationship between the two. There is a correlation, but there's no causation, right? And then we're going to go ahead and test in how significant is that relationship. That's why we talk about explaining one or the other. Height can explain shoe size to some degree because that is true. As someone gets taller, we expect their shoe sizes to increase, but it doesn't mean height is the sole causation of shoe size. And I think that's what we really need to differentiate in here. Okay, so let's just go ahead and go right into drawing and interpreting a scatter diagram. So a scatter diagram is just a graph that shows a relationship between two quantitative measurements. And they're represented in the first quadrant, right, the x and y axis, and each explanatory variable is plotted on the horizontal axis and the response variable is plotted on the vertical axis. And what these essentially are just ordered pairs in the first quadrant in the x and y axis coordinate plane. So we start with the study. I'm going to use this throughout the course. And so here are a list of values of the depth at which drilling begins. So they're drilling 30 feet down and then they're going to start to drill. Here they're real low. They're real down there, right? They're 190 feet down and then they will begin to drill rock. The time it takes to drill in minutes. So here's the minutes it would take to drill 5 feet of rock. So the researchers wanted to determine whether the time it takes to drill a distance of 5 feet in rock increases with depth at which the drilling begins. So depth at which drilling begins is the explanatory variable. X and time in minutes to drill 5 feet is the response variable. So when it says time to drill, all they're drilling is 5 feet of rock. Here is where the depth begins. So they start at 35 feet and it takes 5.88 minutes to drill 5 feet. Let's take this one. So 120. So they are starting at 120 feet down and it takes 7.47 minutes to get 5 feet of rock. What is a lurking variable? I know, like, it doesn't ask that, but what is a lurking variable? So if we think about drilling rock, like something hard, if it breaks really quickly versus it's kind of like a jawbreaker, right? Versus a lemon head. Like a jawbreaker, like if you have a jawbreaker, it takes a while to break it down, right? But a lemon head is you take it and you kind of and it breaks, right? So what's the difference? Why would a lemon head be quicker to break down than a jawbreaker? Right? And really it's the density. It's hot. Well, it's definitely one's more chewier and one's hard. Exactly. So a lurking variable here, maybe the density of rock at certain feet are denser than others, and maybe not. Maybe it doesn't even matter how deep you go. Maybe it's just the environment that it's in that is dense or less dense. So we should probably note that. So a lurking variable, meaning a factor we should take in consideration when we're interpreting our results later on, right? So a lurking variable, it could be, is the density of rock. Okay, so how we're going to just plot this is literally just take every x value here, and then that'll be my x coordinate and y coordinate. So go ahead and plot those on the scatter plot. I'm going to use a thicker marker. And so 35, so which is right in the middle here, and 5.88, so maybe about here. Okay, and then 50, 5.99, 75, 6.74. Okay, so that's what it looks like. And we can see, if I scroll up a little bit more, we can see there's different types of relationships between the variables, but we can see in this case, let me make a little note. We could see as starting as start depth increases, like overall, right on out, if we looked at all of the data here, we could see that it's moving upwards left from right. So that would mean like as the starting depth increases, um, the time it takes to drill 5 feet also increases. Okay, so we're going to have, there are different types of relationships. There's many because there's a lot of different functions out there. So we call a relationship linear when the points on a scatter diagram follow the pattern of a line. The relationship of nonlinear are when the points follow a general pattern but not a line. And then a relationship has no correlation when the points do not show any pattern. So either they can show a pattern of a line or not. Even though they don't show a pattern of a line, they may show other patterns that we've seen before. And so if we scroll up to the next page, I just put a couple there. So the first one, linear, we could see the same kind of relationship as with the drilling rock, right? As X increases, Y seems to increase. In B, it's also linear, but as X increases, Y decreases. But still, we could see that they make a pattern of a line. Notice C is nonlinear. So it doesn't make a pattern of a line. Does it mean it doesn't make a pattern? It does make a pattern, right? We've seen this before, like with X squared, it's called a parabola. This looks like my little 4-year-old went and just put a bunch of dots on the paper, right? And that just means there's just no relationship and no correlation. So in this class, we don't have to worry too much about all these different types of nonlinear. We're just going to do linear in this class, and you'll probably be observing other types of patterns in your research methods class. So we say, and let's look at A here, we know that as X increases, Y increases. This is called a positively associated relationship. It's when above average values of one variable are associated with above average values with the other variable, and below average values of one variable are associated with below average of the other variable. That is, if two variables are positively associated, if whenever the value of one variable increases, the value of the other variable also increases. And this is what we had with our rock example. Negatively associated is exactly what we have here, right? It just means that essentially the same type of rationale, except as the explanatory variable increases, the y value decreases. And so and that just means there's a negative association. And sometimes that's okay, like especially right now, the coronavirus 19, the COVID-19 virus, as the number of people get sick, we're looking for what, like, the number of vaccines go down, or the number of people sick as days go by. as days go by, right, as days increase, the number of people retrieving the COVID-19 virus is going down. So that's a negative association. Is that a good thing? Absolutely. So just because some two variables are negatively associated, it doesn't mean necessarily a bad thing. The positively associated is things like if the number of hours a student studies increases, their scores on their exam also increase. And that's a good thing, right? It wouldn't be a good thing if the number of hours students study increase and then like their exam grades go down. We wouldn't want a negative association with those two variables. But there are in cases where we would want negative association between the variables. Um, and then some positively associated.